My distinct pleasure to introduce Professor Yossi Gilad, coming from Hebrew University. Yossi has had a long interwoven history with BU, from coming over actually as a student for an exchange with in my lab for a short period of time. Then he came back and worked with Sharon Goldberg and his other people. And it's nice to see him come back as a respected professor.
Thanks for the kind intro, and start the talk. Okay, so this is a project we started kind of a while ago, and we're still kind of getting new results. But the whole motivation for it was that we wanted to build a very metadata-private communication system that gives you.
Yeah, you just do me a favor and press OK.
Oh, yeah.
Thank you.
Okay. So we wanted to build this metadata-private communication system that has a very strong privacy guide. So what I mean by that is that if Alice is communicating with someone, exchanging messages, then an adversary observing the network and even controlling the servers in the system shouldn't be able to tell which user Alice is communicating with, if any. And we were sort of targeting text messages, so very short communication. And there's a long history of work in this area. And so, very broadly speaking, the different, maybe three types of systems you could sort of imagine. So the first ones are based on Tor, which is essentially doing onion relay routing. So those will do not cannot give any privacy guarantee when the adversary controls the network. But performance is very good, and in particular, the server's work, which is kind of what we're worried about in our work, is very light. It's linear in the number of users. Yeah.
So what do you mean? I mean, Tor does provide some guarantees, even if you have local network. It's got some side channels.
Yeah, I mean, you could see a message kind of being sent and someone receiving a message shortly after. So you could do this in these.
You could do some correlations. Yeah.
Right. So okay, so it does give you something, but in our threat model, it's considered broken. Okay. Yeah. So another thing you could do is you could have mixed nets where users send messages and then servers mix them in kind of some order to unlink the sender from the message being sent out of this mixed net network. So here, also pretty efficient on the server side, but there is some trusted server in the system. So if they're all malicious, then it's pretty obvious to the attacker which user sent what message, right? Because they can just do the reverse permutation, figure out what happened. And then lastly, there's a kind of a recent line of work doing private information retrieval in the context of these systems. So here, we're going to get into the details of these PIR protocols, but generally speaking, the servers do more work. So in particular, they have to do kind of a quadratic work given the number of users. So this is less scalable, but all the servers in the system can be co-op, and still you get privacy. Okay. Yeah.
Is this like assuming that everyone sends at most one message?
Yeah. So we're gonna have a bunch of kind of boundaries and limitations around communication. In particular, it's going to be synchronous, and everyone can only send at a fixed rate, just to avoid the timing cycle. Okay, so this work is basically about kind of alleviating the load on the server side. So we save about an order square root in the number of users. And the way we do it is we basically kind of build a distributed variant of PIR where the server can outsource the heavyweight computation to anyone, to workers in the network, and then it can also verify that those workers did correct work. So given this distributed way of doing things, now we're going to apply it in the context of communication, and basically we're going to have the clients do the work. So those clients are going to be our workers. The server is going to distribute the load, the computational load, onto these clients, and they're going to work hard to save, to remove the bottleneck from the server. Okay, so first off, let's describe the communication model, just so everyone is on the same page. So we're going to communicate through this one server, presumably one server. You could have more than one server, and it's trivial to shard. Let's assume that there's just one server. All users send messages to that server, and then they do it on kind of, the messages are fixed size, and the communication is synchronous. So the user sends one message per round, and that hides whether they communicate or not, essentially. So regardless of what they do, they keep sending this message. And they send it, they write it, they sort of tell the server, hey, write this message into a particular address. Yeah.
Just want to point out that if you do that, you obviate the problems with Tor that you were mentioning as well.
So this makes Tor kind of, you get to this mixednet type. So UI. Well, except that Tor doesn't actually mix, right? So you still you see a message, you see the order of messages coming in, you know that they come out.
You don't know which messages are coming out because you're doing
just because of order. So let's just, I assume that there's some correlation between the order you get messages and
depends on the network latency.
Yeah, it depends on the. I agree, it's noisy. Mixed-nets do this just deliberately kind of mix messages too. But I agree. Okay, so we're gonna have this synchronous communication, and also each user has an index they got from the server, and they write their message every round to the particular index. Okay, so far so good. Now to retrieve a message, this is where we're using PIR. So then every user is going to have a PIR query that essentially the server processes against all messages that were stored for that round, and then gives a response, a private response to the user. So essentially, because everyone writes at the same round, every round, then this unlinks this tells the server which user wrote what message, but when we read through PIR, so the server doesn't actually know what user reads which message. Okay? Yep.
How does the recipient know who sent them a message?
Yeah. Okay. So that's they wouldn't know. So in this particular protocol, there's a separate dialing protocol that's a little bit more heavyweight that allows them to start a conversation. So essentially, this dialing protocol, there are a bunch of folks doing it, but you could use a variant of PIR called keyword PIR to also implement that. And that essentially allows two users to coordinate. It's a little bit more expensive. So the way we're going to do it is basically you coordinate every epoch that covers multiple rounds. And then that gives you, that allows you to learn your body's index. And then you send the PIR query for querying that particular index that stays fixed for the epoch. And in every round, the server is going to evaluate all PIR queries it has for that epoch against the new messages that were received. Right? So you keep reading, essentially you keep reading privately from the same cell. The server doesn't know which cell, but it's the same one. So you keep reading a message from your body.
And the indices don't change.
Not in a particular epoch. So every epoch, the one thing is that they have to be sequential for PIR for this PIR to work. So basically, users can come and go, but only at epoch boundaries. Right? So then at the beginning of the epoch, the server says, okay, you're number one, you're number two, and so on. And if you want, if some users go offline, fine, but if they want to join, then they can do it next.
I just had a quick question about the indices roughly. So these kind of correspond to the user, but in an epoch. Did I get this right?
It's not. So these are not secret, right? So when a user writes a message, the server knows which user that is, right? So you don't like to hide the fact that Bob wrote the particular message. So the server knows, okay, Bob has index number 3. There you go. Here's the message.
But it's essentially the user identifier for an epoch.
Yeah, except it has to be sequential. So okay, so that's the only thing. So you could imagine an array of starts. Okay. Okay, so another thing is we're going to assume that any users that two users that exchange messages have some kind of shared secret they exchange out of band, and they can use that to encrypt their messages end to end. Right? So maybe when Bob deposits a message, they also encrypt for others. Yeah.
If everything is encrypted, why not just have each user download the entire list of messages each time, and they can only decrypt what they can decrypt?
Yeah, no, you can absolutely do that. So the only reason is it's expensive. The whole PIR kind of theme is we're going to save on bandwidth.
The communication is the bubble.
So we
didn't list communication in the.
Yeah, no, you're right. So this does better than the you could do PIR just by downloading the entire database.
Exactly.
Yeah. Always, for sure. But the idea is we're going to do better than that.
Okay.
But that would be considered like quadratic in your model, right? Because the
But
single
not-
server would have to
Oh, you just
Yes,
the
but
database to all
it's
users.
going to be quadratic, but in communication and I mean, if you're quadratic in communication, then you had to do some computation to send out the message.
The computation is done anyway. Like the PIR table is being generated anyway.
This is
So you just publicize that, and anyone can go and download it.
Yeah, but to download it, they have to connect with like a TLS connection or something. I don't know.
I mean, you have to download each slot. So like
All the
presumably,
users.
when you send something, I mean, like theoretically speaking, you do some work. So if every
Yeah, but it's
user downloads
linear in the number of users.
per
There's no
user,
quadratic.
no, it's per user. Right?
Each user has a constant amount of work, right? I
No,
download.
each user
table size
downloads
is not
the
constant.
n users. Each user downloads a table that has n slots for each user. So it's something like across all users per user. It's the negative. Okay. And then finally, we have the adversary, right? So this adversary can basically observe all network communication, can do whatever it wants with the messages. It can control the server, so the one server that we have, and any clients except the two that we might want to exchange. Okay, so it's pretty powerful. Basically, it controls everyone except the two users wanting to maybe exchange messages. So the starting point for this work is basically kind of viewing PIR as matrix multiplication. So I'm going to describe pretty simple PIR protocol. Then there are variants you can do, like a recursive PIR and many things that are slightly more efficient. And in this talk, we're going to have this basic PIR protocol where the database of messages is basically a squared matrix, right? So if we have n users, then it's square root of n by square root of n. And then the server arranges that. So basically, if Alice speaks with Bob, she knows what index in this matrix belongs to Bob. She knows what to query. And then she generates a query. So how does she do it? Well, her query is, naively speaking, is a one-hot encoding of the column where Bob's message is. Okay, and it's each entry in that query in the square root of n vector is encrypted by a kind of a homomorphic scheme. Okay, so each entry is a bit. It's either 0 or 1 encrypted under some key that Alice chose when she generated the square. So this is kind of naive. In practice, you could do better. So the query doesn't have to be a full-blown column vector. You could use the homomorphic properties of the encryption scheme to send just a tiny. It seems wasteful, right? So you have a vector that tells you what column Alice is interested in, and it's encrypted. But we're also using homomorphic encryption. So you could think of it as like, and maybe Alice sends the index of what she cares about encrypted, and then the server homomorphically expands it into a whole column. In practice, we're using this compressed version. Okay, and then why does this look like matrix multiplication? So if the server database is this matrix, and the user's query is this column vector, now, well, the server can compute the matrix vector product because it's homomorphically encrypted. And if you sort of do the math, essentially what comes out of here is the column vector where Bob's message is. So then you can think of it as like the response is a column vector, and then Alice gets this column vector, and she does exactly what Alice said. So she can remove all entries that she doesn't care about, just take the message that she does.
But now you're doing fully homomorphic encryption as part of your PIR, so now it's really not very practical. Is it?
No, it's pretty practical. Yeah, you could do it except for this compression trick. You could do it with just a kind of a linearly homomorphic encryption, because you could essentially treat the database entry as a constant, and then you just need to sum up encrypted cycle times, encrypted data. The thing is, so if you want to really save on bandwidth, like you might say, well, this column vector, I still don't want to send it. It's too much. You could do the same thing recursively. So if you wanted to recurse, now you can do this linear homomorphic. You need the fully homomorphic scheme to save even more.
In this setup, because you're compressing the client query, why would you make the matrix be squared? Shouldn't it be wider than it is tall, so that the response is
no, so it depends on how many times you want to apply this PIR scheme recursively. If you only do it once, then having a square matrix is optimal.
No, I mean I don't understand how, because you're compressing the client query, so that part is like log of square.
Well, the compression is kind of, this is fast decompression, right? So the server is going to need to expand.
Yeah.
Right? And so I guess what you're saying, well, maybe it's just one entity.
I'm saying, like, make the number of rows in the matrix be 1 and the number of columns be n.
Okay.
Okay, so then
Yeah.
the client query is almost the same size because it's compressed. The server's work is still big O of n, which is the same as what it was before, but the response size is much smaller. It's now big O of 1. So why don't you do that?
Let's see. So you want to expand the client's query to a full n kind of an n size. Yeah, well, okay. So this compression, for a bunch of reasons, it doesn't give you the full blown compression factor that you think of. In practice, you could only compress, depending on the particulars of the fully homomorphic encryption scheme, But with the schemes we use, it's like a factor of 4,000. So you could compress quite a bit, but it's at the end of the day, it's a constant and both. So, but I mean, you're right. If you keep the query fixed, then you could expand it.
I guess I'm just asking, is there any other reason why
Yeah.
the database matrix needs to be square? Or is it just to optimize the?
No, so
size?
usually you talk about the square matrix because you're not applying compression. So that's kind of the main thing. If we were, I don't think it would have fit in like just one element that you're thinking of more. And the other thing is you could apply it recursively.
Okay.
So, okay, so what's next? Okay, so if we had multiple clients, then each of them sent a column essentially, and then you get, so this column is on ciphertext vectors, and so you get ciphertext responses. This is the way we do matrix multiplication. So the one issue here is that the server really processes the entire database for every query. Okay, so to do this multiplication, at least kind of naive multiplication. So you could do maybe better, but it wouldn't save you a whole lot because of this homomorphic encryption. The constants are not that great to use, like Strassen's algorithm and all that. In practice, people end up using the naive multiplication. So the server has to do a lot of work. Okay. So instead, what we're going to do is we're going to have the server arrange clients in groups, and each group is going to take a subset of the yeah. And so the way we're going to do this is we're going to split the work across clients. Is the server is going to send a row or maybe several rows to each client, right? And then that client is going to compute their row against all the queries that they get. Okay, so basically they're going to do a vector multiplication. So that's the sharding plan, right? So the first thing we need to do is to argue that it's safe. Right? So the server was doing some processing before, processing, and now it gives clients data. The reason about the privacy that this method still gives, right? But if the server was oblivious before in this PIR scheme, then it couldn't have given any information to the clients it outsourced the processing to, right? But this, I mean, if I'm oblivious, I can't actually teach anything. So I think at least they at most the client could get is the server's view, right? So even if the server gave everything to the client, then okay. So now what about liveness? So those clients, well, when we had one server, then liveness wasn't really that big of a deal because I'm deploying this system. Okay, I have my server. If the server's down, the system's down, fine. But all users need to do is basically trust that the server is online in order to communicate. But now, maybe you have 1 million clients, and one of them might be bad, basically. And if that client doesn't return the right response, they can basically cheat on whatever computation that they do. They might not do the computation, send some junk instead. And then they might they might prevent others from communicating, right? So kind of intuitively, you you might think, well, okay, maybe that's not too bad. So users, Alice and Bob already share a key. They can do some sort of authentication, add a mark to their message, and now the recipient can just verify, right? They can verify, see that they got a co-op response, and then complain, right? So you still want to kick them out, the bad client, because otherwise they're going to keep on co-opting communication for future rounds.
How do you figure out who the bad client is?
Well, okay, maybe the server does the computation. You complain, then the server does the whole computation. Even naively, right? So you receive a message, it has a bad authentication. You know that something is up. You complain to the server redo the computation, and kind of compares responses, right? So this whole kind of product calculation that the clients do is deterministic. So in theory, the server could repeat it. It's not the most efficient way to do it, so we're going to get into something that's more efficient. But if you do that, even if you don't care about performance, then even that is problematic, because when you complain to the server, you essentially reveal to the server that you received a co-op message, and the server might do it on its own, right? So it might see the database of messages. Oh man, I really want to know which person that Bob speaks to, so I'm going to co-opt this message and see who complains. Okay. So instead, we need to somehow detect that a message is invalid, but without any feedback from the recipient. Okay, so this is what we're going to do. Yep.
Is this the same security requirement of like, there's some recent papers on like maliciously secure PIR. It sounds like a selective failure attack is what you're protecting against.
Yeah, I think it's similar in some aspects, but also different in other ways. So I think you could apply the same ideas you have from there to this setup, but I think it might be a little bit less efficient, just because they care about. Well, okay. I mean, I think the one thing where the models differ actually is that when you those papers basically essentially assume that the client retrieving data has some kind of commitment to the entire database, which in our case they don't, and then they sort of verify the response against this commitment. We don't have any of that. I think we looked into those papers, and still I think you could augment it and apply some of the ideas, but they're more meant to the case where you have really one server computing the response. I don't think they quite work with this setup, although I don't have I can't really pinpoint the reason for this type of efficiency.
But your threat model is there's like one main server, and then now all the clients are kind of also acting as for the server.
They might. So ideally, I want to kick out if some client is misbehaving, they return a bad response. I want to kick them out for future rounds.
But
maybe
the main server semi-honest then, or
it depends. We distinguish between safety and liveness. So for safety, meaning for keeping users, for keeping privacy, that server doesn't need to be honest. They can essentially do whatever they want. Still, they can't learn how to communicate with whom, right? But for liveness, you sort of can't really do it. I mean, you communicate through the server. The server can just drop all messages and then break availability. So we can't achieve more than that, right? So the idea is, for liveness, we only want to trust the server, not those clients that we outsource work to. Okay, so luckily with this view of PIR being matrix multiplication, you could apply ideas for efficient matrix product verification. Right? So in particular, you could could look into the Frival's algorithm. So this is maybe algorithms one kind of technique, right? So what actually happens in Frival's? Well, you get the input is three pieces. In our case, M, the message matrix that the server has, Q, the query matrix, and then there's this response matrix, which is all the results that clients return, right? And the server wants to check whether the product of M and Q is R. Right? So essentially, if all clients behave correctly, naively, we're going to augment this soon, but let's say for now. Right, so what does the server do? Well, it chooses this random vector, this random challenge vector, and then it computes the product of the response by this vector and also the queries by this vector. And then the result from that is also a column vector, and then they can multiply the message matrix by this vector. So essentially, this server, instead of naively speaking, it would do a matrix multiplication. Now it does only matrix vector multiplications, which is more efficient. Okay, and then it checks for equality. So we want to apply this sort of technique.
Isn't there a probability of failure then?
There is a probability of failure. You can drive that down either by repeating this or by having a challenge vector that is not just bits. So if entries in C have more the integers, then it's essentially like doing this multiple times. So you're right, though. There's some failure probability needs to be kind of reasonably low, right? Because look, it doesn't have to be cryptographic security, but still, you don't want to just blame someone for speed or have some misdetection. Okay, so first challenge is we don't want to work on full matrices. So when a client responds, we want to be able to verify the response very quickly without dependency on collecting the responses from all other workers. So how do we do that? Well, given our kind of workload distribution method, this is actually not that difficult to do. So there are some things, basically 3 blocks here. So the first one we can do ahead of time, right? So the server can choose this challenge vector, can calculate the product of Q and this challenge vector, the query matrix and this challenge vector, just keep it stored for the entire epoch. So that is one thing that they do, and they're done with it. And this is for all clients. Yep.
That was my question. You do this once per epoch for each client.
So-
It's n operations per round, but you don't care because they're always still.
So you could, yeah. Oh, well, if you do the entire query matrix, then you do this once for all. This part you can do once for all clients. Then the second block is something that you do per client. So you basically take the message vector that they have, and then you compute the product with whatever you get from the first step. Yep.
So here the matrix Q is the queries matrix. Isn't that encrypted homomorphically with a different key for each column?
Good. Yeah. That's okay. That's you're getting ahead a little bit.
Okay, I'm sorry.
So I'm gonna talk about it in the next slide. Yeah, that's difficult. You're right. Yeah. Okay. So you're doing this calculation for every client, for every round. And then the only thing is once they respond, now you can just compare, right? So simple enough. Okay. So what's going on here, right? So how do you even do this calculation? you're right. So we said earlier that in PIR, every client chooses a different public-private key for their query. And so, first of all, if you're doing these homomorphic operations, unclear what is it that you're going to get because you're adding up things that get encrypted with multiple public keys. It's kind of weird, right? The second thing is that the server doesn't even, it can't even decrypt, right? So, okay, even if everyone chose the same key, and that makes the calculation coherent in the ciphertext under the encryption, right? Even then, the server doesn't have the private key, so they can't decrypt and they can't detect equality. So this, the maybe surprising thing is that doing this calculation that I showed you earlier, the Frival's protocol, doesn't require homomorphism per se. So what does it require? Well, it requires some algebraic operations in the ciphertext space. So for that, we really don't care about the homomorphism. We really just care that all ciphertexts are in the same ring. And then you can, all these arithmetic operations kind of are well defined, and you get an absolute zero at the end. So if things are equal, they look exactly the same. Okay. This is ideally what we thought. Turns out it doesn't quite work this way. So in order for what I just said to be true, you also need this extra property, which is that you need associativity in the ciphertext space. Right? So you need this, and this is basically Frival's, right? So this is the matrix R, basically. So you need this equation to hold, and in order for that to hold, you need the ciphertext to be associative. Turns out that not all schemes give you that. So this unrelated. We need to use FAG just to be able to do this compression, and we need the homomorphism to do the PIR calculation. So we have to have an FAG scheme. But not all FAG schemes give us the algebraic properties we need in order to do the Frival's verification. So initially we were using BFV. So this is a pretty common scheme. Unfortunately, it doesn't have this, so it rounds numbers when you encrypt, and that makes it non-associative, basically. Luckily, there's another. Oh, we kept studying these schemes. So a scheme that does have this property is BGB, and so we could use that one for our implementation. And the nice thing is about when you have this validation technique and you combine it with the way we sharded the work, well, now the server can also detect when the client gives an invalid response, right? So if the server runs this Frival's protocol and for some client the validation doesn't work, right? You're not dependent on other client responses, and so if validation shows an invalid response, the server knows, they know exactly which client was malicious, and now they can kick them out, they can punish them in some way.
Sounds like a great denial of service.
Right? So
Well, if I want this client not to be involved, I corrupt somehow their message to the server.
are you the, no, wait, are
You
you?
said a global adversary, so I could be on the network, I could be.
Oh yeah, but yeah, I mean, you control the network, you can just,
Well,
I kick them out, yeah. Just like disconnect them. You're right, though. Yeah, we sort of assume that, okay, the adversary is present and they have the network. But yeah. And all these connections are TLS, so essentially, if you want to do something like this, you really have to be on.
I just have to corrupt the signature and then the server will think you're
I
being malicious and then
agree.
it'll punish you.
You can totally do it, and then the server. I mean, depending on the punishment, right? So maybe okay, maybe you don't want this super serious punishment where the client has to pay so much, but what you could do is you could not let them communicate, right? So you could say, well, okay, that client, they didn't behave, so I don't let them write messages now. And
I could use it to reduce the number of clients
Yeah.
in the system.
exactly, so you sort of remove them and save the work for the server. Yeah. Okay. So we implemented this, and we built on top of this library called PIR. So PIR used the BFV scheme, then we had to kind of replace that.
It's nothing 3,500 lines of code.
It's not too bad, right? I mean, there's pretty good infrastructure. I agree, the students were happy. They didn't need to implement all that much. Okay. So then with this prototype implementation, we wanted to evaluate performance and answer key performance matrices. Right? So what's the latency? How do we scale? How does the bandwidth requirement look like? Okay, so we deployed this at our university's compute cluster. We had 100 machines. So one machine was dedicated to the server. These are relatively weak machines. So one machine was dedicated to the server, and then we ran instances of the clients on the other machine. So every machine had more than one client, basically. So the first thing is, how long does it take to do epoch setup? All right, so that sort of informs the number of rounds you want to have in an epoch. If setup takes long, then you need more rounds in an epoch, which means that you can change your body, give it longer intervals, right? So how long does it take? Well, so each of these lines represents a different size of a database. So you can think of it as like there are maybe 2 to the 16 to the 18 and so on users in the system sending messages. And then the x-axis is how many clients does the server handle in terms of how many PIR queries does the server processes against this database. So the idea is, well, we didn't have a lot of resources. And in practice, maybe you have multiple servers processing a different portion, each of them processing a different portion of the user queries, or maybe you have a more powerful server, whatnot, but this is sort of just to evaluate. Yeah.
So one more question on users and indices. So you talk about users here. Is an index one user per epoch, or is an index one user in one communication? So if I talk to Ari and Gianluca, do I get 2 indices, or do I count as 2 here, or do I count as 1?
Well, you would have 2 indices, but so basically this assumes that every user has just one
communication.
Right, because if you can have multiple, then you sort of leak how many, at least what's the maximum you have, right? So you have to, I mean,
Pair.
Yeah.
There's no
Yeah.
communication.
Okay, so you see on the y-axis, it takes orders of the order of tens of seconds. So that means that for say 1 million users, we would expect the number of rounds in an epoch to be at least several minutes. Right? Okay, so what about latency? So in this graph, we wanted to show the asymptotic performance. Right? So the more users you have, that means that you have more message writers and message readers. So there's some. This is where the quadratic cost comes from in the original PIR schemes. And so to simulate that, as we increase the number of clients, we also proportionally grow the number of messages in the database. Maybe I should have reversed that to match the lines here. But the idea here is that we're going to have twice as many more processors here than on the previous. Yeah.
How does it compare to trivial PIR, like what was suggested before? Just download the whole thing?
Well, no one. I
Like,
think
let's say we set up a BitTorrent or something and so they can share the work of distributing. Does it take-
Yeah, I
'cause
mean,
it-
maybe
You said it's 256 bytes per message, so
per message, right? And so you have
it's like a few megabytes to download them.
Well, okay,
For
let's
a
see.
million.
So for a million, right? For a million users, you'd have 256 megabytes per user to download. Right?
Does that take 50 seconds to download?
I don't know, for one server, I mean, you could even, okay, it depends on how you do the download. We didn't have like a peer-to-peer network where users share.
But
Yeah, I mean, maybe you could have a super efficient, yeah, I mean, that could be, you know.
okay.
I think having peer-to-peer is more challenging maybe, but also I don't know how this would continue to scale, right? Okay.
Three data. So it's
Yeah. Oh, and another thing is that when you encrypt, it's 256 bytes, gets larger. So I mean, okay.
Does it? No, because you have this. You're saying there's a shared symmetric key for the.
Yeah,
each
but you
pair?
have to. Well, when you take a fully homomorphic encrypt, you take this query vector. Right?
No, but
Then
I'm
you-
saying that in the trivial one, you don't have to use
you're
that
right. You're
feature,
right. You're right. Yeah. Then you just download the symmetrically encrypted database and.
That's why
Yeah.
my students sometimes
So
the
you
link
could-
list is good enough.
So depending on how you do communication, I think if the server has to send 256 megabyte times a million, I don't know, but you have a more efficient way of doing it, maybe. Okay, so what about the bandwidth impact? So here we sort of cap the client's bandwidth on the x-axis and then see the impact on latency. And for two different database sizes. And so you can see that when the client has at least 40 megabits per second speed, then impact on latency latency stops being impacted, right? So that means that's roughly what we expect the bandwidth requirement to be for this database sizes. Yeah. Okay, so just wrapping up now. So we have this distributed PIR that lets a server outsource its PIR work to clients, right? We are using Retrieval's algorithm or a variant of Retrieval's algorithm to efficiently validate those clients. And then we also have a prototype implementation and show that it asymptotically and concretely scales better than the previous work. Yeah, okay. That's it. I mean, it's been fun.
A couple of questions, if anyone has any other questions.
No, I have one more.
Yeah.
So maybe I missed something like so Freivalds check is like a column vector, right? That the server chooses a random vector, column vector, and then the queries themselves are also like compressed column vectors.
Yes. So once you decompress, you get a column.
Okay, and I just maybe just missed it, does the servers, like does the Freivalds column vector, does that thing also need to be encrypted? Does that need to be secret or is it?
No, it's like a constant, basically a constant. Like you treat it as a vector of integers.
Okay. But do they send this to the clients and have them do the check or the server?
No,
does
the
the check?
server does it. So
Okay.
basically that's how the server checks the client. It keeps, if that challenge vector is exposed, then the client can efficiently compute the response that passes the check, but
Right.
junk.
Okay, so they never actually, because the server doesn't have to prove it to anyone else, so they never actually send the challenge vector out, they're just kind of like
Yes.
doing that on their own.
Yes.
Okay.
All right. Thank you.
Thank you very much, Yossi. Yes.